Hi guys, thanks for joining. Sorry. Let me take care of that. I don't know. So what is happening today? So batch gradient descent and stochastic gradient descent, all these things are there. எங்க முடியாது என்ன அவங்க வீடெல்லாம் வச்சிருக்காங்க. They're all well off. These guys are having a lot of money. See, importantly, they have. They don't have any pollution there. That is one of the key advantages for them. Yes. Hi Swati, thanks for joining today's session. I think others are busy. No one has joined. Other guys, I called them. They said that they are busy with Christmas activities. There are some bad jobs are running. That's the reason. Let's wait for some time. At least if two or three more people, if they join, will continue because it's
Yeah,
been going on and on, right?
yeah,
Almost 1 year is going. 2020 is going to get over.
yeah. It's okay if
Let's wait for
as
some
more
time.
than if
And
somebody else tries to continue. Otherwise, it's
5 minutes
fine.
time to get started. So am I audible to you?
Yeah, yeah, you are. Can you hear me? Hello.
Let me just shake off my. Yes, I think some problem. Yes, then it is good. If you are able to hear me, it is good. Ideally, if you people also should be able. I should also be hear your voice. We already device. I don't know what problem I have it in my system. Let me just reconnect it. So is it audible now? Yeah, I think some problem is there from my side. Anyhow, let me continue. In case of any questions, you just type it in. Yeah, so let's wait for 3 to 4 minutes, Swati. Otherwise, we will resume next weekend. Next weekend, being a long weekend, I think you will not be available, right? So we'll see about others' availability. Next weekend is festival, Christmas. Yeah. Prior. Hey Prakash, good that you joined. Prakash, am I audible? Am I audible, Prakash? Hello, hello. Just type it in the chat window. I'm not able to hear. I think some problem with my settings, the mic settings. Okay, 1 second. Just let me just check what happened. I did not make any changes to my settings. Mm, net access and okay, I muted it here. That's the problem. So yeah, I think I should be able to hear now. Prakash, I muted it from my side mistakenly. The sound, right? The sound I muted. The speaker thing I muted it. I think I should be able to hear now. So anyway, I think we can continue, right? So others, if they join, let them join because we are running short of time. Almost we are going to very close to 2020, right? So we are drawing closer to 2020. Today, if I cover it something, we will cover the rest of the thing in the next weekend. Since next weekend being holiday for you all, but except me, we have to work during weekend also. Anyhow, let it be there. We have some people. Most of them are available from my side also at US in USA and other places. They can cover me even if I don't join because last year I was part of the Christmas and other thing. Even Cyber Monday, even Black Friday also I contributed a lot, right? So hence I can give excuse for the upcoming weekend. I'll wrap up as much as possible. Next weekend the plan is continuing with the convolutional neural network recurrent, the deep learning part. Okay, don't miss out next weekend. It's very interesting topic, deep learning, and that one. Once I finish this, I'll try to complete the NLP part also next weekend. Okay, as much as possible. Probably one more session is required, right? Saturday, Sunday plus one Saturday is required. Okay, so that I can wrap up everything. But the next Saturday is going to be this problem, right? Yeah, good. So this weekend we have 27 and 28. 27 and 28. Yeah, probably January 2nd we will wrap up everything. Okay, all put together. Fine, we'll get started. Okay, we'll get started. I will continue with continue recording this. So, any good news with the assignments? You just try the assignments. Okay, this weekend I will help you to review the assignments next weekend. Hope you'd have gone through the assignment solution link which I shared with you from my website. Right, in my website I shared the link. So that is how you need to document after you complete. Once you build your model, you need to extract the insights by analyzing the model's output. Okay, and then you need to come up with some kind of recommendations. What kind of action plan the stakeholders can take by with the with the output, whatever you are getting it based on the analysis. You can recommend what kind of action plan they can come up, or what kind of remedial measures they can come up. Okay, so that is the one you can do it. So anyhow, you just go through on my link which I shared it for the housing price prediction. Okay, fine. So now we'll jump into understanding what is artificial neural network. This is very important topic because artificial neural network is the one forms the basis for deep learning. Okay. So, okay, the neural network have been taking the artificial intelligence world by storm. If you have noticed neural networks, right, that have been used in a diverse set of domains like language translation, rather, right, the language translation, healthcare, and speech recognition, face recognition, logistics, even in object tracking, especially using deep learning algorithms, we can track the objects also, right? So the neural network is a game changer, I would say. This is the one, neural network is the building block for our deep learning algorithms, okay? And also, the one of the important salient features of the neural network is, very well, the car, the self-driving car, right? There are many end-to-end deep neural networks also used for the self-driving or autonomous cars, autonomous driving, right? Autonomous or self-driving car. So in the case of self-driving car, right? So the input to the algorithm or the camera images. Okay, they have camera. These cars are bombarded with many sensors. All right. So what this algorithm, the machine learning algorithm, right? What it does is it takes the camera images as the input, and it predicts the steering angle, right? Which angle the steering should be turned. Okay. So that this is very critical. In case of any inaccuracy, if this overturn, what will happen? Gone. It bangs with the nearby car, right? Anything can happen, right? So in the case of the self-driving car, also they used the advanced machine learning algorithm like the deep neural networks, convolutional neural networks, so on and so forth. Convolutional neural network is also one of the the popular neural network and widely used neural network algorithm as part of deep learning. Using convolutional neural network, we can do image classification, and we can do some kind of object tracking. Even in the case of convolutional, there are different variants are available like RCNN and fast RCNN, faster RCNN, mask RCNN, like different algorithms are available. Anyhow, in the subsequent weekend, we will take a look at what is convolutional neural network. First, let us understand what exactly convolutional neural network. I'll help you understand it, and also we'll understand recurrent neural network. Using a recurrent neural network, you can do the next word prediction. So it's right. Most of us, we when we do the when we do some search in Google, right? We type the keyword. Even when we wrongly type the keyword, right? It tells us, is this what you are looking for? Suppose I want to see the best deep learning study material. I want to search it. So I just type best deep space learning space study, and if you before even you type, it suggests are you material something, right? Next word prediction and all. You can do it using recurrent neural network, and also you can do forecasting. Hope you remember time series. As part of time series, we discussed about forecasting, right? So we discussed about auto-regressive moving average, and also we discussed about ARIMA, right? The same thing you can do it with a recurrent neural network. With the recurrent neural network, the accuracy is much better. So that's what anything you do in deep neural network, the accuracy is very good. But again, so if the data volume is not that much, we can go ahead with a machine learning algorithm. But one caveat is, if you are going to use the deep learning algorithm, you need to have lot of data to train your model. Okay. Okay, and let us see what are the types of artificial neural network. We have something called feed-forward neural network and convolutional neural network. Convolutional neural network is for the feed-forward neural network is the conventional one. Okay, the traditional neural network algorithm, and you have this one, the convolutional neural network that is meant for image classification. Okay, image classification. And recurrent neural network, as I said, RNN, it is also called as RNN, the short form. RNN is to do the next word prediction, and also you can do the time series analysis, like what do you see? The forecasting. You can do forecasting with recurrent neural network, and you have something else, LSTM, long short-term memory neural network. This also the LSTM is a type of neural network. In that case, right, the memory cell is incorporated into the hidden layer neuron. Okay, the traditional neural network, you don't have any memory. Anyhow, don't worry about LSTM. We'll discuss about LSTM also as part of a recurrent neural network. And we have something called op field network, op field network, uh, op field network. Sorry, I should have updated it. Op field network and Boltzmann machine. We have something called Boltzmann machine. Boltzmann. So these things falls under. This one is for unsupervised. In the case of deep learning, also you have something called supervised and unsupervised, and these two falls under supervised machine learning. And in Boltzmann, the restricted, they also call it a restricted Boltzmann machine. Restricted Boltzmann machine. This one falls under unsupervised machine learning algorithm. Okay, and we have something called modular neural network and clustering neural network, association neural network. Like with different types of neural networks are there. First, let us understand what exactly the neural network is all about. Okay, before we try to understand what exactly the neural network, right? Sorry, the deep learning, all the things. Let's try and even the neural network, artificial neural network. Let us try to understand what is biological neural network. Okay, so the motivation behind the motivation behind the developing or using the neural network algorithm is, see, using computers, we can do we can solve complex problems, we can solve arithmetic problems, right? We can solve complex arithmetic problems, and any repeated task, we can automate it. You can do everything using computer. But when it comes to reasoning or reasoning out certain things or making decisions based on some situation, right? Uh, machines cannot machines cannot outperform human brain. Okay, so what scientists they thought in the past was, why can't we make or develop an algorithm or system which can which has the ability to simulate the human brain's functionality. Okay, mimicking the human's brain functionality. Is there any way we can, if we can implement it so that the system can make decision on its own, like I showed you in the case of self-driving car? You are just sitting in the car, right? So he's, look here, he's not at all doing anything, he's not at all touching the wheel, the steering. Is not at all touching the steering, right? The system takes care. It's all because of the neural network algorithm, right? We are giving the brain to the system, right? The algorithm is a brain for this system. So, like a driver, the algorithm makes, look here, it's fantastic, right? It turns the wheel very nicely with higher accuracy, right? And you don't have to do anything without human intervention. He is just simply sitting here. He is not even touching this one. Right? So the neural network with the, yeah. So the whole idea here is give the brain to the system. Let the system can think and act like a human being. Right? So that is when the the neural network algorithm came into play. Right, they started thinking about implementing this one. So that is when the neural network, they implemented artificial neural network. Before even we understand what is artificial neural network, let's try to understand the biological neural network. So in our brain, right, we have different sections. Other one is front lobe and temporal lobe. This is called your cerebellum. This is called your occipital lobe. This is called your parietal lobe. Right. So each lobe or section has its own functionality. For example, the frontal lobe. This is the one is helpful in terms of reasoning it out. So if somebody says something, we reason it out, right? Whatever he says is really correct or logically correct or not. And even for our body movements, this is the one is playing a crucial role. So if you could have noticed the senior citizens, right, above 65 or 70, there will be some kind of involuntary movements. Though they don't shake their hand, the hand will shiver, right? So due to aging problem, right? So it's all due to the functionality of the frontal lobe. Okay, frontal lobe is responsible movements and reasoning, problem solving, and similarly parietal lobe. This is the one is responsible for the orientation, right? Movement orientation, the recognition, like voice recognition, right? Whether these voices related to so and so person or not, and perception of stimuli. And temporal lobe is responsible for memory, auditory and visual part, and temporary, right? And temporary lobe and temporal lobe. There are two things are there. And we have something called auditory cortex. This is the one is responsible processing auditory. Whatever I talk, in your brain you have auditory cortex. That is the one processing my information, right? Whatever I talk, right? This is the one is responsible for understand my talk and processing. The visual cortex is, it helps to visualize. Just audio is not sufficient, video is also important, right? So with visual cortex is responsible for, oh, this appearance or this image is related to so and so person, this image is related to so and so person, right? So when we look at these, let's take for example, when we look at the sports person or the celebrities, when you look at their face, you can tell very clearly, hey, he is this person, right? So it's all because visual cortex. For the computer vision, the motivation for the computer vision is visual cortex. Just giving the brain is not sufficient. In the case of self-driving car, if you give the brain, all right, or if you using artificial neural network, now we are able to give a brain to the car or system, so that it can make decision everything on the fly. So when the car is on the highway, if it encounters any hazards or any issues, right, it makes decision on its own, like how a human driver makes decision, whether to slow down the car or whether to divert the car or whether divert the object or stop the car, something like that. All the decisions are taken on the fly. But giving the brain is not sufficient. It should be able to see, right, what object is approaching the car, right? So that is where the computer vision is coming into play. Giving the brain is not sufficient. You need to give the vision to the system also, so that the system or the car, in this case, right, the car can recognize who is who is crossing the road, and what in the case of traffic light, right, whether it's a red light or green light or amber light, whether should I stop or whether should I prepare to stop, or can I start or can I move the vehicle, right? It's all decided based on the visual thing, because the car is bombarded with a lot of sensors. The sensors learn the data from the external world, and it feeds the data to your algorithm, which is there in your system, in your car, and that is the input to your car, right? So the car, the algorithm decides based on the color of the light whether it can start off the vehicle or whether it has to stop the vehicle, right? Everything is taken care. So it requires a brain as well as it requires vision. So the visual, see, the brain's functionality is nothing but our artificial neural network. They mimic the brain's functionality by implementing the artificial neural network, and by giving the vision to the system, right? They simply mimic the visual cortex functionality in our brain. So why a lot of hype around neural networks? So initially they started something called electronic brain, and they developed something called perceptron, right? So perceptron in 1952, and later on they developed something called Adaline. See, neural network is not a new algorithm. It has been there since long time before even we born. Someone, they came up with the idea of implementing neural network. Initially, this is how it evolved. Okay, it started with brain and perceptron, Adaline, and what happened after Adaline? They were posing issue with exclusive OR problem. They are not able to solve using neural network. They are not able to solve the exclusive OR problem. Okay, so you know very well in computer, right? So we have in the computer logic, we have something called AND gate, OR gate, exclusive OR gate. Right? Those are the foundations for the computer logic. Right. So what exactly exclusive OR is, right? The exclusive OR is actually OR but not AND. Right? Exclusive OR is. Let me just. OR but not AND. Right. So not AND, not AND, not AND. So this is what exclusive. They're not able to solve the exclusive OR problem. So that is when this neural network algorithm got died. So people started, they discontinued using neural network, because using neural network, you can solve and or, but you are not able to solve exclusive or problem. Hence the neural network algorithm died. Okay, and no one were using this algorithm. So hence this is called your dark age. Okay, and later on, what they did, some other people, right, they did some kind of breakthrough in terms of solving the exclusive OR by introducing multi-layered perceptron, okay. And then as part of the year, something called back propagation. With the back propagation, you are able to reduce uh, the error, model error, right? So as I discussed you as I've been discussing, right, if you have a machine learning model, one of the key objective of that one is to reduce or minimize the error as less as possible, as low as possible. That is one of the key objective of implementing the machine learning algorithm, right? So, but when it comes to neural network, they used multi-layered perceptron, but still, it is a feed-forward neural network. But the accuracy was not that good. So what they did, they did some other breakthrough by introducing something called back propagation. We'll discuss about back propagation little later. So with the back propagation, they are able to increase the accuracy like anything. Okay. So next one is in 2006, around 2006 or so, the deep neural network gained a lot of momentum. So as I told you, right, on the deep learning algorithm, we have, as part of deep learning, we have different variants of deep learning algorithms are there, like convolutional neural network, recurrent neural network, restricted Boltzmann machine, autoencoder. Likewise, many algorithms became popular because of this one. One reason is the one reason being the hardware cost became very less, and also the breakthrough in terms of developing something called GPU. How many of you are aware of GPU? GPU stands for graphical processing unit. Right? There are some significant breakthrough happened on the hardware side also. Okay, the see look here, 2006 itself, right? The deep neural network, everything was available because of some hardware capability, hardware limitations with some hardware, right? So we were using CPU. We have been using CPU processor. CPU processors are not capable in terms of processing deep learning related algorithms because the deep learning algorithms are a CPU intensive process. It involves a lot of arithmetic operations, right? So hence what they, right, even in the case of 2000 or 2005 or so, right, even the deep neural network algorithm, so deep learning algorithms were not that popular because of the limitations with the hardware, and even the CPUs were not capable enough in terms of processing the deep learning algorithms. It took a hell lot of time. So later on, what they did, they developed something called GPU from the hardware, NVIDIA, right? So NVIDIA, there is a company called NVIDIA. If time permits, you can Google it. So they are the one, right? They developed something called GPU. GPU stands for Graphical Processing Unit. Right? One GPU is equivalent to 100 CPU. Right? The processing capability of one GPU is equivalent to 100 CPU. So with the advent of the CPU, now we are able to use deep neural network, deep learning algorithm. Deep neural network is nothing but the deep learning algorithm. Okay. So that is how the artificial neural network and deep learning algorithms evolved. Okay. So now with multi-layer perceptron, we are able to solve exclusive OR problem, and we are able to increase the model accuracy with back propagation, and also with the deep learning algorithm we can perform image classification, object tracking, image segmentation, like many advanced image processing, and even the word prediction, everything we can do with the deep neural network with higher accuracy. Okay, now let us understand how our brain learns, right? Our brain is much more powerful, okay, than systems or machines. Okay, it learns first. You see, when somebody talks something or somebody explains the concept, we learn it and then we process it. We'll try to understand what he says, right? We try to understand the concept, and then let's say if you see somebody, right, let's say your friend, your classmate, you met your classmate almost during your school time, and suddenly you happens to meet her in a mall. Okay, she bumped into you, she bumped onto you in a mall, right? And suddenly you are she is trying to recognize you, but you are having difficulty in recognizing, but still you are able to process, oh, this face, these eyes, and with these features, oh, she must be so and so, or this guy must be so and so, right? You are able to recognize the objects, and this is how our brain works. So in our brain we have something called neuron. This is called neuron. It's all very tiny thing. You cannot see it with your eye just like that. Okay, you need a microscope, a macroscope or microscope. You need to what is, you need to magnify that 15 to 20 times also, so that only you can see the uh, neurons. Even in the case of even in the case of animals, and even in the case of fly, millions and millions of neurons are there in the brain. Even in human, right, even 100 billion or 100 billion neurons are there, like this 100 billion neurons are. As people tend to age, the neurons will die. So that's the reason why they have difficulty in recognizing people, and they cannot respond our questions, rapidly, right, in a much faster manner. Okay, because some neurons. So these neurons plays an important role. Okay, so look at this one. This is the neuron. Okay, and this is called your neuron, and this is called this branch kind of thing, right? So look here, these are the branch kind of, these are called your dendrite. This is the one is responsible for, this is the one is responsible receiving the signals from other neurons. Look at this one neuron, this is another neuron. As I told you, 100 billion plus neurons are there in human brain. Okay, so in this case, each neuron, all right, this is the anatomy of each neuron. This is what your dendrite, this is the one is responsible for receiving the signals or information or accepting the input. Okay, and this is called your cell body. This is also called as soma. This is the one after receiving the input. This is the one processing the input. Something like, right, our eyes, through our eyes, we are receiving the input. We see some people, let's say in a meeting, 5 people are there. We invited 10 people, 5 people are there. We are able to get, the input using the dendrite, and then we are processing the images using soma, right? So it tells us, okay, how many people are there? 5. How many we called? We invited 10, but only 5 are there. And we have something called axon here. So this is the one is responsible for transforming or turn the processed input into outputs. Okay, this is the one is responsible for that. This is the one is processing. Soma is responsible for processing input, and it transform the processed input into output. That is the role played by axon. And we have something called synapses. This is called your synapses, right? So this is the one kind of a bridge, right? This is the one is responsible for contacting with other neurons, right? The communication happens between one neuron to another neuron is happening via synapses. This is the connecting bridge. Okay, using synapses only, the information is passed from one neuron to another neuron. It is basically electrochemical, okay, electrochemical contact between neurons, right? So the axon is actually, it is used to transmit the signals to other cells are nothing but in this case, right, the neurons. So okay, you understood enough about our neuron. I'm not going to talk in depth about the biological neuron. So hope you understood. In brain we have different sections are there: frontal lobe, temporal lobe, visual cortex, cerebellum, temporal lobe, so on and so forth. And also in brain we have billions and billions of neurons are there. This is the anatomy of the neuron. So it has something called dendrite. Dendrites are responsible input, and axon is responsible for converting the input to output. And this is the one is processing the information. At this moment, if you remember, that is more than sufficient. So this is what our artificial neural network. Biological neural network we discussed a while back. And this is what our artificial neural network. Look here, this is a neuron. These 3 circles are neurons. When this one is also a neuron, the green colored one. Let's say you are passing 3 variables as an input to your neural network. So what is a perceptron? Perceptron is a very simple single layer neural network. Perceptron is a simple single layer neural network. Look here, I have age, income, and just simply passing it as an input, and it will emit an output. Supposing I wanted to predict with this given age, income, and debt to income ratio, whether this customer is going to default, whether is he going to make the payment or not, right? For this, I'm going to pass these 3 variables to my neural network. My neural network model has to predict the class level, whether yes or no, right? It has to produce either yes or no. Okay, So look here, each circle is, this is your input layer. This is called your input layer, and this is called your output layer. This is called your output layer, and each circle is called your, sorry, this is your input layer, this is your output layer, and these are the three inputs passed in your input layer: age, income, depth. And what happens is, before it produces the output, the predicted output, it performs two actions. It's very important that you need to understand these two steps. In the first step, what it does is, look here, this is this connecting line, right? This connecting line is synapse. You remember in the case of this one, right? This is the one is synapse, right? The communication happens between one cell to another cell is via the synapse. Similarly, this is what the synapse, the these lines are synapse. This is the connecting line. Okay. These are the input neurons. Age is an input neuron. For each and every input variable, a neuron will be assigned. Okay, a neuron will be created. This is one neuron. This is another neuron. Three neurons are the three input neuron. This one output neuron is there. In between, what happens is, right? You have synapse here. So what happens is the neural network algorithm, it assigns weights to each and every input variable. W1, W2, W3. It assigns weights. It assigns weights to each and every input variable. Let's say the weights are W1 in this case for age, and W2 is the weight for income, and W3 is the weight assigned to my input variable depth here. Okay, input neuron depth here. So what happens in these two steps, right? So each and every input values are multiplied by its corresponding weights. Age into W1 plus income into W2 plus existing debt into W3. And this value will be computed. And then in step 2, what happens is 1 divided by 1 plus e to the power minus z. What is z here? This is what the computed value of this one, right? The computed value got stored here in z. So you need to find out the exponential value for the z. Supposing if you compute this value, right, your z is, let's say 10. So 1 divided by 1 plus e to the power 10. So what happens is, in simple term, it performs the sum of the product for each and every input and the corresponding weights. It performs the weighted sum, okay, weighted sum in step 1, and then it applies the activation function. This is called your activation function. So what is the activation function here? So how many of you remember 1 divided by 1 plus e to the power minus? This is what called a sigmoid activation function. This is called your sigmoid activation function, right? So we discussed about sigmoid activation. When did we discuss about sigmoid activation function? During logistic regression, right? In the case of logistic regression, we discussed about sigmoid activation function, 1 divided by 1 plus e to the power. You remember in the case of sigmoid activation function, right? We discussed about the probability value should be lied between 0 and 1. 0 and 1, right? So in case the values are less than 0, negative values, if the values are negative, or if the values are more than 1, right? By applying the sigmoid activation function, what it does is it squashes the values between 0 and 1 only. Supposing you are getting minus 0.2 or you are getting 2.7, right? So what happens is it converts 2.7 anywhere in between 0 and 1. And if it is negative value, right, it converts as 0 here, 0 and 1. Anything beyond 1, anything less than 0, right, will be, anything less than 0 will be converted as 0. And anything above 1 is converted in, anywhere between 1 and 7, right? This is what we discussed as part of logistic regression. Please, revisit my logistic regression video, okay, so that you'll be able to recall. So first you need to find out the weighted sum, and then what you do is apply the activation function. These two steps will be performed. But this activation function can be anything. It need not to be sigmoid activation function. You have something like Eve side activation function, ReLU activation function, Likewise, different activation functions, other TANH, something like that. We'll discuss about that little later. At this moment, right, try to understand if I say or anybody says perceptron, right, it is single layer neural network. You have input layer and output layer. But the problem with the perceptron is, as I told you here, right, it cannot solve the exclusive OR problem. What do you mean by exclusive OR problem? Let us just look at what is the OR gate, right? So OR gate, that is the computer logic, right? Supposing you have something called true or false. I just put it like this, okay? True or false. And true or true. Let's say I'm creating, this is a truth table for or, okay? True and true is true or true is true. True or false. When you one of them is true, right? Hence it is true. False or true is any one of them is true of these two, hence it is true. And false or false, both of them are false, hence it is false. But if you draw a line here, you can separate truth and true and false, right? By drawing a single line, you can separate these two classes, right? Similarly, in the case of AND gate, there's something called true, false, and true, false. Right? You have something called true, false, and in this case, true and true is two T's or T, right? T and T is T, and D and F is false, and rest of them are false, right? False. Here also you can, by drawing a single line, you can separate both the true and false. By drawing a separate single line, you can separate the falses and trues. But when it comes to exclusive OR, what happens is, for example, in the case of exclusive OR, I'm going to write true or false, true, false. Nice. And true will become false in the case of exclusive OR. Will become false, and this will become true, and this becomes true, and this becomes false. But if you draw if you draw a line here, right? If you draw a line here, and it is not separating both the false and trues, right? You need one more line to separate the trues and false, right? This is called your exclusive OR problem. So using perceptron, they are not able to solve the exclusive OR problem. Instead of using single layer perceptron, they used multi-layer perceptron. See, single layer perceptron, as I showed you, right? There's something like this. You have some neuron and you are your output layer, right? Instead of this, you can have something like this. And you can have something else like this, okay? Or you can have something like this. By having the multiple perceptron, you can solve the exclusive OR problem. Okay, so that is the reason why I told you, since the perceptron Adaline was not able to solve exclusive OR problem in the past, the neural network became unpopular, right? It was not popular because people thought, what is the point in using perceptron? It cannot solve the classification problem, right? In this case, what happens is, right, you need to, right, it is not separating the linear separable. This is called linear separable. It is not able to separate linearly, right? So by drawing a single line, it should separate it, but it is not separating it. But with the help of multi-layer perceptron, now you are able to separate this one. That is when the neural network once again it became popular. Okay, after introducing multi-layer perceptron. So perceptron. So now let us take a look at the multi-layer perceptron or feed forward layer. Both of them are same here. Look here, in this case, I have something called input layer and I have something else called hidden layer. Hidden layer. And also I have the output layer. This is my output layer. The input, in between the input and output layer, we have the hidden layer. So we have the, 1 second, so Yeah, this is what my hidden layer, right? This is what my hidden layer. This is what my input layer and output layer. So in the hidden, so input layer, for example, age and income. So you might be wondering what is 0.05 and 0.10. Let's say we have done some kind of the standardization, normalization. You remember I discussed about data normalization as part of clustering algorithm, right? This is to convert all the input variables into a single unit of measure, right? So in this case, assume that the data is normalized. This is age and this is the income, and this one is connected to this, the hidden layer first neuron, and this one is connected to this one, and this one is connected to this one. So in the case of multi-layer perceptron or feed-forward layer, every neuron in the input layer is connected to every other neuron in the subsequent layers. Instead of saying input layer, right, every neuron in the neural network model connected to every other neuron in the other layers. We can say that way. Okay. So this one is connected to 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 this one, and this one is connected to this one, this one is connected to this one. Okay, now let us try to understand. Look here. So what happens here is I have assigned a value for these weight W1 as 0.15, and I assign the weight for this one W2 as 0.2 and W3 as 0.25. See these values, you might be wondering what is 0.15, 0.25, 0.30 and zero point 0.2 and 0.40 and 0.50. Right? These values are randomly initialized by the algorithm. We don't have to use any formula or anything. Okay, it is assigned by the algorithm or the model by itself. We don't have to use any. There is no formula for this one. Okay, it is randomly assigned. Then the next question is here 0.30, why 0.30, here why 1.15. Let's say I have two features here, right? Here I have income and age. Let's say that way, right? So in that case, whichever feature that has higher predictive power, the weight will be more, right? If you find a higher weight for a specific input variable, that means that variable is important, right? Significant in terms of including in your model. So this is the one, right? Similarly here, okay, these weights are randomly assigned. Okay, we don't have to use any formula to assign it. This is taken care by the algorithm. But for each and every synapse, what is synapse? The connecting line between the input layer to hidden layer and the hidden layer to the output layer. Okay, these are all called your synapse. For each synapse, the weights are assigned randomly. I don't know why my system is hanging suddenly. Yeah, so this is my for each and every synapse, right? So even for this, the weight is assigned. For this, weight is assigned, and we have something else called bias. Please notice very clearly. Note down very clearly that bias is there, right, for the hidden layer and the output layer. So why bias is introduced? Uh, Bias is very much important because you remember, like in the case of linear regression, logistic regression, we use intercept. It is somewhat similar to intercept. It is somewhat similar to intercept. You remember in the case of the sales, right? Sales and advertisement example. I gave you advertisement example. If I don't give advertisement, that doesn't mean I don't have any sale. Even though I don't give any advertisement, still sale is happening. But if I give advertisement, if I expend money on the advertisement, how much increase in sale I can expect? That is where the slope coefficient is helpful. Whereas in the case of the intercept, right, intercept coefficient, that is helpful. In the case of the slope is 0, what is the estimated average sale of your Y, right? That is what it. So you just think at this moment the bias is nothing but your intercept. It is very much required, right? So this bias is connected to this one and also this one. Okay, sorry, a line I did not put it here. Even this connected to this hidden neuron. Okay, so in this case this is connected to this one, and even for the bias the weight is assigned by the algorithm. So in this case let us assume that the weight is the weight assigned was 0.35 and the weight assigned for this bias was 0.6. Okay, so here in the case of hidden layer, what happens is there are two steps are carried out. So it multiplies the input value with the corresponding weights. So the 0.15 into 0.05. Look here, that's what I put it in detail here. So W1 into the input 1. I1 is input 1 plus this W2. So this W2 into I2. This is input 2. W2 into I2. W2 into I2. Okay. One second, my system is hanging. Suddenly it is hanging. Sometimes it happens. Yeah. So this is what. Okay. One second. So this is what I'm saying. Okay. W2 into I2, right? So W2 into I2. And if you look at your 0.15, right, into 0.05, 0.15 into 0.05 plus 0.2, this one, look at the blue color. Okay, for this the weight is 0.2. 0.2 into 0.10 plus the bias. You need to include the bias, 0.35 into 1. Okay, and if you add all these things, you get 0.3775. In step 1, you need to compute this weighted sum of this one, and in step 2 you need to apply the activation function. So this is my value for the z, right? Z is equal to sum of xi into wi, and 1 divided by 1 plus e to the power minus 0.3775. If you open an Excel sheet and if you find out exponential exp of minus 0.37, you will get this one. So the output of this hidden layer first neuron is 0.5936992. Okay, and similarly, if you look at the second one, right? So W3, look at two red colored one, right? This one is connected to this hidden layer and this one is connected to this hidden neuron. So W3 into I1 plus W4 into I2 plus 0.35 into 1. If you solve the 0.3925, in step 2, you need to apply this z value. This is my z value. You need to apply this. You need to apply an sigmoid function on this one. When you apply this 1 to 1 plus e to the power minus 0.3925, you get some value like this. So for this hidden neuron, you got some value, and for this hidden neuron, you got some value. Listen very carefully. This is very important. Okay, very simple one, right? Don't ask me the activation function is sigmoid function. Don't we have any other activation function? That is, we'll discuss it later. Okay. At this moment, you assume that we have used the sigmoid activation function. Okay, but you can specify. Okay, you can override this value also. Instead of using sigmoid activation, you can use other activation functions like tanh or heave side, relu, and so on. Okay, but in this example, for illustration purpose, I used sigmoid function as an activation function. There are two steps carried out in the hidden layer, right? In the hidden layer neurons. First, it performs the weighted sum, and then next it applies the activation on the weighted sum. Okay. The next thing is here also it has to perform the same thing. See W5 into out H1, and look here in the 0.40 into 0.593. So this is the one is we got from this one, right? So 0.40 into output of this one. What is the output of this one? 0.593. What is the output of this one? This is the one, right? 0.596884378. I don't know why it is hanging suddenly. Just give me 2 seconds. Something is messed up. Right, so this is how, look here on the right bottom, right, W5 into out H1. Out H1 is nothing but the hidden layer, the first neuron, the H1. The H2 is hidden layer, second neuron. Okay, that is what out H2. And the output of this one is nothing but 0.593. This one into 0.40. And for this, the output of this one is after applying these two functions, right? Steps, right? You get 0.5968888 into 0.50 plus the bias is you need to take this bias 0.6 into because we are dealing with this one, right? I don't know why it takes. Yeah, this zero point 0.6 into 1 is equivalent to 0.055. The next step is you need to apply the activation function. Even on the output layer, you need to apply the activation function 1 divided by 1 plus e to the power minus 1 point. Sorry, in this case, yeah, 0.5. It is not 0.055. I think it is 1.13575. Okay. So if you compute the value for the exponential value, you will get a 0.75689. Okay. So let's say assume that, right? In this case, it's a classification problem. The output layer, it assigns the probability. There is a 0.75 probability that this customer is going to default. Okay. And but the actual is 0 and 1. 0 is non-defaulter, 1 is defaulter. Okay. If you subtract the predicted probability 0.756899 from 1, you can get the error, right? The remaining one is your error. That is what your error. 1 second. Look here, that is what I did it here. So total error of the neural network, this is 1 by 2, right? So 1 by 2 into target. Target is nothing but the predicted value minus the output is the actual value squared, right? This is the mean squared error. And 1 by 2 into, let's see the predicted values, let's say, the predicted, okay, in this case, sorry, the actual is 0.01 and the predicted is 0.75. Okay, and there is a mistake here. 1 second, let me correct it now so that there should not be any confusion. See, actually the target is the predicted one, the output is the actual one. Okay, supposing let's see the target is 0. Or 1, right? So 1 minus 0.75. And if you solve, let's assume that you are getting, this is what my error. This is what. The predicted probability was 0.75. There is a 0.75 probability a customer is going to default. But how accurate the predicted probability is, right? So the one is the actual output. One is defaulter, 0 is non-defaulter. So you subtract this one. Right. Ideally, if this value, right, the probability value is somewhat closer to this one, that means the accuracy is good. Instead of 0.75, had we got 0.95, that means the error is less, somewhat closer to this, right? So that is what it says. Hope you understood, right? So this is the predicted probability. This is the actual output, right? In my data set, for each and every customer, in the last column of my data set, I have zeros and ones. Some customers were flagged as zero, some customers were flagged as one. Zero means they were not defaulter, one means they are defaulter. Supposing, let's say in this case, this customer is a defaulter, 1 minus, what is the predicted probability for this customer that he is going to default? 0.756. So 1 minus this 1.27, this is the error. Okay, this is how the error suppose. This is called your feed forward multi-layer perceptron neural network model. This is what is happening under the hood. Okay, in the case of neural node, this is what is happening. So what is the big deal here, right? So the next question is, how many hidden layers should I use it? How many number of neurons should I use it in each hidden layer? Should I use only one hidden layer? Can I use more than one hidden layer? Yes, you can use more than one hidden layer. When it comes to deep learning algorithm, deep learning also called deep neural network, right? As you introduce more number of layers in between the input and output layer, we call that as a deep neural network, because this neural network has many hidden layers. Hence, it is a deep neural network. In the case of deep learning algorithm, we use more number of hidden layers. Why do we have to use more number of hidden layers? Because to improve, to perform more complex transformation, right? And also to improve the model accuracy, we use hidden layer. We'll give you some example during the time of explaining the convolutional neural network. You'll be able to understand. Okay. At this moment, let's not worry about can I introduce more than one hidden layer. For interview purpose, yes, you can introduce more than one hidden layer. Each hidden layer can have more than one neuron also, more than two neuron also. What is the formula for this one? There is a formula for this. We'll discuss this also later. Okay, let us not get into formulas now. Yes, you can have hidden layer, multiple hidden layer. You can have one or two hidden layer also. How do I determine how many number of hidden layers are required? For that, what we do is we have something called hyperparameter tuning, using which we can find out the optimal number of hidden layers. Can you use two hidden layers? So this is one hidden layer. Likewise, you can use another hidden layer. It can have two neurons. Another hidden layer, another hidden. Likewise, you can introduce multiple hidden layers. The question is, how do I find out the optimal number of hidden layers? How do I know, or how is there any way if I can find out how many number of hidden layers should I use it? Because if I use too many number of hidden layers, also problem. Sometimes it doesn't make any sense. The training time will take longer time, right? So if I introduce less number of hidden layer, also problem. How do I know how many number of hidden layers that I have to use it? For that, we perform something called hyperparameter tuning, using which the algorithm can tell us, okay, use this many number of hidden layers. Okay, you don't have to break our head there also. Okay, it is all plain vanilla. Okay, fine. So far so good. Right now you understood what is feed forward layer, because it feeds the input values from one layer to the subsequent layers. Hence it is called feed forward layer. Here we are using more than one perceptron. Look here and here, and we are using more than one perceptron. Hence it is called multi perceptron feed forward layer. Good, everything is good. So using multi-perceptron, we can solve exclusive OR problem. Good. That way also it is good. Now, this is the error I'm getting at, 0.278. The question is there any way can I reduce this error further? The lesser the error, better the accuracy. That is what is expected. When you join as a data scientist with any company, the business stakeholders or your CEO or your reporting manager will expect you to reduce the error as low as possible so that your accuracy will be very good. See, take for example, in the case of stock market, if you are buying these stock, right, the equities in bulk, what will happen? Even if there is a minor, even if you lose 1 rupee per share, supposing you are buying 100,000 shares, even if you lose 1 rupee per share, you're gone, right? The prediction accuracy is very, very important. Just because you say, right, I improved my model accuracy, everything, and with that, my models forecasted stock prices, this is the one, right? So by going by his word, or going by his forecasted stock price, and if you buy too many shares, and per share if you lose 1 rupee, let's say the stock price is 2000, let's say hypothetically let's say 200 rupees per share, okay, but you forecasted the share price can go up to 201 rupees. So what you're doing is, if I buy, you have more money and you want to buy 100,000 shares, right? If that goes 201, if I sell it, so 100,000 into 1, I can get that much of profit. But actually what happens is, you invested, let's say you bought 100,000 shares, and next you invested on the 100,000 shares. So what happened at the end of the day? Each share, you lost 1 rupee. So 100,000 rupees you lost. So now you understood the importance of the accuracy, right? The accuracy is very important. There should be, the minor difference, like, per share, 0.25 paisa if you lose it, or 0.101. So, the actual and predicted or forecasted is very minimal, then the loss is less, right? Now you understood how important. So now the question is there any way I can reduce my error, error further down? Okay. So what happened in the past? They used the multi-layer perceptron. Since using this, they are able to solve exclusive OR problem, but the accuracy was not that impressive. That's when they developed something called back propagation algorithm during 1985 or so. So after they introduced the back propagation algorithm, they are able to increase the accuracy like anything. Okay, that is also the reason why the neural network model became very popular in the case of, yeah, comparing with other algorithms. Neural network became very popular because of the emergence of something called back propagation algorithm, right? Back propagation. What is back propagation? Let's see, the error is 0.278, right? So in the output layer, this is the predicted output, and you subtracted from the actual value. This is what the error. What happens is you propagate this error back to your previous layers, right? You send this error back to this one, and then adjust the weights. By adjusting the weights, see, the weights playing the important role, right? The weight plays the crucial role here. Look here, the weight is 0.25 and zero point 0.3 and 0.35 for the bias. This is the weight. With these weight, and you are getting 0.59, right? With these weights, you are getting 0.75. Is there any way, if I can change the weights in such a way, I can reduce the error? Is it possible to changes or adjust the weights in such a way to reduce the error? That is where the back propagation comes into play. So here we are back propagating the error to the previous layers till the input layer. Okay, from year to year we are back propagating the error. By back propagating the error, in the sense we are going to adjust the weight here, right? And here, instead of 0.40, try with some other number, with this, with the different weights. Are we going to get, are we getting lesser, are we getting a decrease in the error? And similarly, right, here also we are making changes to the weights. The algorithm, not we, the algorithm may, we have to make the algorithm to, as part of the back propagation, what it does is it changes the weights randomly, right? It changes the weights, it adjusts the weights, and see if it is trying to reduce the error. By iteratively, what it does is it changes the weights from the input to hidden layer to input layer. It keep changes the weights for all these things. Okay, see, in this case we have only two input neuron. You assume that in the case of image, right, images are viewed by the algorithm as the pixels, right? So let's say 25 cross 25. Your image size is 25 cross 25. 25 is height and 25 is width. So 25 and 25, how much? 625, right? 625 neurons will be there. One, two, three, like 625 neurons will be there. You can see a lot of crisscross lines here, and a lot of neurons will be there here and there, right? When you do back propagation, what will happen is, right, the weights have to be changed correctly here and there, right? And the algorithm, right? So the back propagation, the whole objective of back propagation is propagate the error back to your previous layers, from your output layer to hidden layer to input layer, and adjust the errors. So adjust the weights, or change the weights, or make changes to the weights in such a way you can reduce this error. Okay, can I randomly change the weights? But if you do randomly, instead of using zero point 0.5, if you use 0.60, and here instead of using 0.40, if you use 0.70, but here if you change it, it will have an impact on this one, right? The previously, right? So is there any technique that is available to systematically adjust the weights? That is where the gradient descent algorithm is used. The interview, they'll ask you, so in the case of back propagation, which algorithm is used to reduce the error? Gradient descent algorithm. We discussed about gradient descent uh, before, right? I just give you a quick recap on the gradient descent which we discussed. It is an iterative optimization algorithm. In the case of, we discussed about linear regression model, right? In the case of linear regression model, the error is actual minus predicted squared. That is what the cost. So the whole idea is we need to reduce the cost. The error is also called as a cost. The lesser the cost, that means the lesser the error, better the model. So that is when we use the gradient descent algorithm. We define the cost function. We discussed about the partial derivative, everything, right? And I spoke about a hill. A person is standing on the hill. There is a treasure here, which is nothing but the lesser here. You need to descend from here to here in order to get the lesser error. Lesser the error, better the model, right? So what we would do is randomly we initialize some values for our beta coefficients, theta naught and theta 1, and then by keep changing the values of theta and theta 1, right, we'll try to reach this place. In order to reach this place, we need to know the gradient. What is gradient? Gradient nothing but the slope. In which direction should I go? If you don't know, so that's why I gave you this analogy. You see, your eyes are blindfolded. You are standing here, and somebody is asking you, and somebody is telling you, hey, in the downhill, there is a treasury pot. Okay, but I'm going to, but you are not allowed to, go just like that. I will blindfold you. If you are lucky, you can go and get it. Your eyes are blindfolded. How can you reach this place? In order to reach this place, you need to know two things, right? One is the step size, another one is which direction. If I keep a longer steps, what will happen? Let's say if you keep a longer step, instead of landing here, you may overshoot here. You may go here also, right? So this is a overshooting problem. Or if you take a slower step, it will take longer time to converge. Convergence is a longer time to get the minimal cost, minimal error. Okay, so how do I, get to this place? So for this, you need to know, for each and every step, you need to know the direction. So can I go in this direction? Yes, that's where the gradient descent is. This part is the derivative part, dou by dou theta j of theta naught. This is your derivative. This is the one is helpful in terms of identifying the slope into some small value, right? Alpha is nothing but, the, it's a learning rate or the step size, okay? This is hyperparameter, it's a tunable value. We can specify any value, small value, 0.05 or 0.001, something like that, okay? You need to multiply the slope by this alpha learning rate, and by subtracting this one from your current position, you can get the next position, right? This is the formula is helpful in terms of getting to this place. What is this place? This place is nothing but the optimal cost. Right? When you come down, when you descend from here to here, the error will reduce. See, in the y-axis, the cost is nothing but the error. As you walk down, 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 what will happen is the error goes down, right? So which direction should I go? I have to come here. For this is the formula is helpful. Hope you understood, right? The gradient, the purpose of gradient descent. So, but here we discussed about what is derivative, what is partial derivative and all. I'll just show you chain rule and all we discussed. See, derivative. The derivative is nothing but the rate of change, right? Simply is the slope of a function. The derivatives are helpful in terms of knowing how fast something is changing. What is the rate of change at any given point of time? Let's say if I move from here to here, how much the cost is going to get changed? What is the increase or decrease in cost? When I go down, when I come here, what is the cost? Right? So that is where the derivative is helpful. And the partial derivative, what is partial derivative? What is the difference between derivative and partial derivative? Partial derivative, if you use multivariable, right? Multivariable, when your function is multivariate, if you're using multiple variable, see, if you are using only one input variable, let's say, take for example, in the case of advertisement, you are giving advertisement only in TV, that is your input variable. Supposing you give advertise in Facebook or Google AdWords, you are using multiple variables to predict your sales, right? TV advertisement and the money expended on TV advertisement, the money expended on Google AdWords and Facebook, right? These three, since you are using more than one independent variables, you need to take the partial derivative. That is the difference from derivative. So derivatives are basically helpful in terms of understanding by taking one step how much the cost is going to change, right? Since we are having multiple independent variables, right? We have to take partial derivative. Using partial derivative also, right? We are able to find out what is the rate of change, right? So for each and every step, we are updating the theta values. Okay. In a nutshell, in the case of back propagation, the gradient descent algorithm is used to reduce the error further. But I told you, I gave you an overview, right? What is back propagation? When I gave you a definition for back propagation, simply by changing the values of the previous layers weights, by adjusting the previous layers weights, we'll find out is there any way, right? The weight is reducing it. It will not happen just like that. You cannot blindly change the values. That is where we'll be using something called gradient descent algorithm. Right? So in the case of gradient descent algorithm, right? In the case of back propagation, when you use gradient descent, there are three steps are there. There are three steps you need to, will be following it. The one is calculate the loss. Nothing but the error, right? This is my error, right? Calculate the loss or cost function, all are same. Okay, error, all these terms are same, but in real time they use cost or loss. Okay, so the loss is 0.27. Calculate the loss, and in step 2 what we do is we calculate the partial derivatives. Calculate partial, because with the help of partial derivative only we will get to know how much the error is going to change if I change the weight, right? By changing the weight with some value, how much the error is going to change, right? You need to use partial derivative of your total error. This is very important. Total error. Calculate the partial derivative of total error with respect to each weight. With respect to each weight. See, to adjust this weight, you need to calculate the partial derivative with respect to W5. And for adjust this weight, you need to find out the partial derivative of your error with respect to W6. For each and everything, you need to take the partial derivative. Similarly, here also, okay? W1. I'm not going to show you everything. I will start with W5. That will help you to understand the rest, right? If I take one example, you'll be able to understand the rest. In third step, what we will do is, importantly, right, we update our weights, perform gradient descent, and update weights. See, first thing is very simple, right? Calculate the loss, cost function or cost. And second step is, how do I reduce this one? using the calculating the partial derivative total error. The total error. This is my total error, right? So to calculate the partial or total error with respect to each weight, and then update the weight, right? Supposing, let's say you are calculating the partial error total error with respect to this W5. Now by using this, right, you are getting 0.39 something like this. So you need to update this weight, right? This is your new weight. This is the feed forward layer. The feed forward, as part of the feed forward, these are the weights are assigned. After applying the back propagation using gradient descent, this weight should get reduced, right? Let's say the weight, right? Maybe, right? It will be, the error will be less. Okay, the error will be less, 392 something like that, right? It need not to be less. It will be, more than also, more than this one also. Okay, I'm just, for illustration purpose, I use this number. Okay, so calculate the partial derivative of the total error with respect to weight 5, and similarly with respect to W6, and then you need to update this way. The new weight. This is called your new weight. After calculating or performing the gradient descent, what is the new weight and what is the new? That is the whole objective of gradient descent algorithm, right? Using gradient descent algorithm, we are obtaining the new weights or changing the weights for each and every synapses, and see how much increase or decrease in the total error. If there is a decrease in the error, then we are good, right? So this gradient descent algorithm is good, right? So there are situations, even after using a gradient descent algorithm, the error may not reduce, right? But there are cases by using the gradient descent algorithm, the error can reduce it. Even if there is a minus decrease in the error, it is good, right? But when you use more number of iterations, you can see an improvement, or you can see a decrease in the error. More the number of iterations when you use it, you can see the decrease in the. And okay, before we jump in understanding, so what I did, I assigned some values for each and everything, and then I took partial derivative, and with that, right, by applying the partial derivative, how it helps us in terms of reducing the weight with some numbers, and by taking the partial derivative, the derivative part, right? I explained it in the subsequent slide. Before we get in there, let us try to understand what are the activation functions. I spoke about sigmoid activation function, 1 divided by 1 plus e to the power minus z, right? Like sigmoid, you have some ReLU, softmax, tan step, and ELU, ReLU, or ELU and leaky ReLU. Sigmoid function, this is what we discussed, 1 divided by 1 plus e to the power minus z. And this is the idea of sigmoid activation function. It squashes any value between 0 and 1. Okay. See, the threshold function outputs 1 when input is positive and 0 otherwise. Okay. And we can use sigmoid activation function, or you can use ReLU, rectified linear activation function. So here, if you look at here, what is whenever your function is less than 0, it gives you 0. Whenever it is greater than 0, the output remains same. What is the difference between the sigmoid activation for ReLU? In the case of sigmoid activation function, any value which is less than 0 or negative value will become 0. Any value which is greater than 1, it will be converted anywhere between 0 and 1, because the probability values lies between 0 and 1, right? But in the case of ReLU, any negative value will become 0. Fine, it is somewhat similar to sigmoid function, activation function, but anything greater than 0 will remain as it is. Now, tell me when is this helpful? ReLU activation function. As I told you in the case of image, right? How the systems, algorithms can understand or see the image. How many of you have seen the Arnold Schwarzenegger's movie? Before Terminator movie came, right? I forgot that movie. I don't know. So in that movie, right, five guys, they goes to forest, thick forest, and they, right, some alien, used to kill all the people in that. Those people they visit in that specific island, right? The alien used to kill, but the alien is not at all visible to the human beings. 1 second, I'm just searching the movie name. I don't know how many. I don't know if you are really. Yeah, most of you may not be a fan of Arnold Schwarzenegger. So in that movie, it's a very nice movie. Okay, and the right. So one of the, not Terminator, before Terminator one movie came. I somehow forgot. It's there on. I could not recollect. Okay, so in that movie, right, you can see human being like red color thing. For his eyes, all the humans appears like a red color thing because the blood is in red color, right? You can see only blood, red color. In one scene, the this guy, the Arnold, right, he jumped into a mud. Since his whole body covered with mud, the alien could not recognize where he is. Though Arnold is very close to that alien, he could not recognize where Arnold is. Though he is very close to the alien, because for his eyes. So likewise, in the case of system, right, the system can understand the image or view the image in the form of numbers, pixels. Supposing your image size, let's take your photo, your passport size photo. If the photo image size is 25 cross 25, the height is 25, the weight is, sorry, the width is 25, right? So fine. So here the pixel values are ranging between 0 to 255. Okay. If it is, I think black is 1 and white is 0. Yeah, different values have different colors. Okay. That is how the system can understand the images using pixel values. The pixel values are the numbers. Okay, the numbers. Right. In the case of image classification, if the value is more than 1, it should not be converted as anywhere between 0 and 1. Supposing if the image, the pixel value is 200, right? It should be 200 only because that could be, some color, right? That number is for some color. If it is 1, it is a black. If it is 0, if it is white. Different values, anywhere between 0 and 255, right? Different values between 0 and 255 has different colors and different things. So in that kind of situation, ReLU is important. There is no point in converting any values greater than 1 here. Hope you understood, right? So ReLU is used. But one problem with ReLU is if any negative values, right? The negative values become 0. So in that case, what happens is it cannot, it cannot read the pattern, learn the pattern correctly. So that's where there's something called leaky ReLU. Right? It introduces a small negative slope, so it does not have a zero slope. This helps speed up training. Range for minus infinity to plus infinity. Sigmoid function 0 to 1. ReLU is 0 to any value, 0 to infinity. And when it comes to leak ReLU, minus infinity to plus infinity. We have something called parametric ReLU. And so let's ignore that one. Okay. We have something called tanh function. So tanh function, it converts the values between minus 1 to plus 1. Okay, and fine, right? These are the activation functions. And we have something called softmax is another activation. We'll discuss it probably as part of, not probably, we'll discuss as part of convolutional neural network in detail, okay? So as of now, if you remember these activation like sigmoid, ReLU, tanh, it is more than sufficient, okay? And next one is the interview question. What is the difference between parameter and hyperparameter? I showed you the weights in the neural network, right? Those are all called parameter. What is hyperparameter? Activation function. So what we can configure, what we can change is called our hyperparameter in simple terms. what is computed by the algorithm or the model is called a parameter. So as I told you, in the case of neural network, the weights are computed by the algorithm, right? 0.15, 0.2, 0.3. We don't have any control here. We cannot change this value just like that. Or we cannot use our own formula to override this. These weights are computed by the algorithm. Like in the case of linear and logistic regression, the values for the coefficients, the intercept and the slopes are computed by the algorithm. Hence, that is called parameter. The hyperparameter is something which we can see. Look here, this is the weighted sum, and then I apply the sigmoid act. Sigmoid, we use this notation, okay, yes, or something like this, okay. You apply the sigmoid activation on function on the z, value of z, right? You can use sigmoid activation function, or you can use something else. What we can modify is called your hyperparameter, and what we cannot modify is the weights, right, or called your parameter. You just remember it, okay. In the case of intro, they might ask you these kind of simple tricky questions. Okay, going back to back propagation algorithm, okay. So now let us try to understand the back propagation algorithm very clearly. I know by using the partial derivative, how we can do this one, okay. Let us assume these values are assigned for the respective weights. 0.15 is assigned for W1 for this synapse, and 0.20 value is assigned for weight 2 of this one, and 0.25 and point, sorry, zero point 0.2 is this one, 0.25 and 0.30, okay, W1, W2, W4. And this is my hidden layer neuron 1. So I used the meaningful notation H1 here. H1 means hidden layer first neuron, H2 is hidden layer second neuron. In the hidden layer, you have the bias also attached to it. And even the case of output layer, the bias is attached. Look here, in this case, there are two output neuron. Now, in the case, see, this is my input layer, hidden layer, output layer. In the case of output layer, I have two neurons are there. So this is point n. So the point n and point one. So I don't know how many of you remember in the case of logistic regression I discussed about, right? In the case of probability, predict proba. You have a function called predict proba in Python, especially in the case of scikit-learn, right? Using which you can find, right? Using which we can see what is the probability a customer will default, what is the probability a customer will not default, right? So okay, the example is there is a 0.9 probability a customer will default. There is a 0.01 probability a customer will not default. There are two values, outputted by these two values, 0.01 and 0.99 are produced in the output layer by passing these two input values, okay, something 0.05 and 0.10. Now we will see how to reduce the error in this case. Okay, in this case, what I do is, you remember, you just recall this diagram. Okay, recall this diagram. So look, recall here you have two sections, right? One is the summation, the input value into the corresponding weight, and similarly this input value into this weight, right? 0.15 into 0.05, zero point 0.2 into 0.10, that is what your z. And once you compute the z, next you need to apply the activation function on the z. Please remember this image very clearly, okay? Don't forget it. The same thing is I'm doing. So what I do is I take only this portion, okay, or these two things, and I take W5 here. W5, W6, W5, W6, right? Yeah, W5, W6, not this portion. W7, W8, I'm not going to include in my example. I included only W5, this portion only, okay? H1 to output 1, H2 to hidden layer second neuron to output 1. This one and this one, I just magnified this one. So you remember in the hidden layer I showed you, right? There are two parts are there. One is your the weighted sum. The next one is the activation function. So here the W5 and W6, W5, W6 and W5, W6, and this is your B2, right? W5 and W6. Only this portion I just chopped off only this portion for you to understand. Okay. So by applying the chain rule, right, we are trying to, uh, adjust the weights here, and we'll see what is the change in the cost. So in this case, right, this is my activation function. There are two functions, and we are two steps we are carrying out, right? One is we are computing the what is that? The weighted sum and the value for z, and next one is we are applying the activation function, right? So let's see, in this case, the output value, I did not mention it, right? Yeah, 0.01 and 0.99. Let's say, in this case, yeah. So let's say, yeah, these values are the weights, right? I just took only this one. Okay, so for this one, right, for this, there are two output neurons are there. In the output layer, there are two neurons are there, right? So here, what I do is, I call this a E01, I call it E02. Error 1 for this one, error 2. So error 1 is equal to 1 by 2 into the actual value minus the predicted value whole square. Similarly for this one, right, 1 by 2 into the actual value minus the predicted value whole square. So error 1 for this one, error 2. I need to find out the error for these two, actual minus predicted, actual minus predicted. So E01 plus E02 is total error. Now I need to find out the this one, right? I need to find out the partial derivative for the total error, for the total error. So how do I find out? How do I find out the total error? Look here, this is what I mentioned it, right? See, calculate the loss, calculate the partial total error with respect to total error with respect to weight. Now we need to calculate the partial error, total error with respect to weight. So what I'm going to do here is, it's very simple if you concentrate here, right? Look here. So I need to take the partial derivative of the total rate, error with respect to W5. But since it depends on the other, output, right? It is not straightforward taking the partial derivative on the total with respect to W5. It is not a straightforward way of doing this one. Hence, what we are doing is simple way of understanding this one is this error, right? This error is produced by the output, right? The basis for this one is the output. This is depending on this one, and this is depending on the z value, right? Because you are applying the activation function on the z value, right? And for the z value, you are using this weight. You remember this weight into this weight into this output of this one into this one, is nothing but your z value, and on top of the z, right, you are applying the activation function. Hence, the error is depending on the out one. So the in this case, one second, yeah. So what we are doing is this dou e total is depending on out to one. We are going the reverse thing, okay? We are taking the partial derivative on the total error with respect to out to one into this out to one is depending on net to one. Hence, we are taking the partial derivative of the out to one with respect to net to one, and net to one is depending on W5. Hence, we are taking the partial dou net 01 divided by dou W5. Right? You cannot compute this value directly. Hence, there is a dependency, right? So dou E01, the total error. So the dou E total by dou out 1, dou out 1, dou net 1, dou net 1 divided by dou W5. This is how we can find out the partial derivative. So in order to find out this partial derivative, it is not that easier. It is slightly you need to do some changes. You need to use different technique here. So what you need to do is here, right? So we know what is error. I'll just show you here. See, the E01, we know that, right? So E total. So first we will expand this one. E total is equivalent to, so 1 by 2 into target O1 minus out O1 was actual minus, sorry, predicted minus actual, right? So we can put it the opposite way. So out O1 minus and both are the same. This is the error, actual minus predicted. Okay. For the error 2 also, right? For error 2 also, we need to find out 1 by 2, the cost function, the actual minus predicted. Target minus out O2. This is target 02 is 01 is 02. Here out O1, out O2, O square. Okay, so what happens is if you take the partial derivative on the E total with respect to out O1, right? So do out O1. First we will go by do out O1. What will happen is, so in this one, right? The 2 into 1 by 2. And how many of you remember this one, the power rule, right? Power rule is this one will come in the front and this one will become subtract 1, right? 2 minus 1. So hence this one will come here 2 into 1 by 2 and target 0 1 minus out 0 1. The 2 minus 1 will become 1, right? So this one will become constant because you are taking the partial derivative of the error total with respect to out O1. Can you see anything out O1 here? Out O2 is there. Out O2 is not at all. Something else is a target, right? Target. Hence, these two values are different from this one. This becomes constant. The constant, hence this is constant. This term will get discarded. Hence, it will become 0. So on 2 into 2, this one will become, so what you are going to get is the target, right? See here what will happen is you will, yeah, into minus 1, right? Minus 1 because you are taking the partial derivative on the total error with respect to auto 1. So what value is multiplied by auto 1? Minus 1, right? Out 1. So though it is not, see, minus auto 1 is nothing but this one is multiplied by the minus 1. Hence the value that got multiplied by this one is minus 1. We need to put this one. So to put it in simple term, with minus of minus, right? Minus 1 minus of target 0 1 minus out O1, right? Fine. So this is let's say the target one is in this case 0 0.01. That is what we got, right? In the previous image, if you look at it, because 0 0.01, right? 0 0.01. And let's say your predicted output is 0 0.075, something like. How we got this value 0.075? Out to O1, how we got this one? Can you guess it? Can you tell me how we got this one? 0.75. This we got because of this one, right? So net O1, right? So Z, the Z value, right? Net O1 is equivalent to W5 into the out H1 plus the W6 into out H2. I told you, right? The output of this one has to be multiplied this one. The output of this one will be should be multiplied by this one, and then you need to add these two things together in order to get the net O1, right? Plus B2 into 1. You remember B2 into 1. In our case, the bias is, I think, 0.6, right? So if you solve this, yeah, if you need to plug in the value here, what is W5? We assign some value for W5, right? 0.4 into out H1 is 0.593 something, and W6 was 0.45. Look here, W6 was 0.45, right? W6 0.5, W5 is 0.40, right? And into the out H2 is 0.59, 0.59. See, if you take a pen and paper, right, and if you apply this for each and everything, starting from here to right, here to here, right, you will get these values. Okay, 0.598 and all, plus the bias is 0.6. So that's what I mentioned, right? The bias is 0.6 into 1 into 1, you get some value, right? So you get something 1.105, something like that. If you apply the sigmoid activation function for right, outflow 1 is nothing but, there are two steps. The first step is find out the weighted sum. The second step is apply the activation function on this one, right? Out O1 is equivalent to 1 divided by 1 plus e to the power 1.105, which is nothing but 0.075 and dot. Okay, that is what I mentioned it here. This is how you can get the value for this one. Okay, the dou e total divided by, when you take the partial derivative with respect to auto 1, this is what, so the what value we are, when we take the partial derivative, the total error with respect to auto 1, right, we are going to find out individually here, right? In this case, if you do it like this, you get 0.01 minus 0.075. So how much? Approximately 0.741, you will get something like that, right? Right, this is what we do it. So next one is, what we do is, since we are using dou e total divided by dou out 1, we are done with this. Next one is dou out o1 divided by dou w5, right? You need to work on this. And dou out o1 divided by dou dou out o1. What we will do is, we will, don't, so dou e total dou out 1. Okay, next one is dou out o1 divided by dou, yeah, this is the one, right? Dou out o1, this is correct. And dou out o1 divided by dou net 201, dou net 01. So in this case, what will happen is out o1, right? We are talking about out o1. Out o1 is, what is this? This is nothing but 1 divided by 1 plus e to the power minus z. In this case, yeah, the out O1 is, we are going to get donate 01, right? So in this case, 1 divided by 1 plus e to the power minus, net O1, right? Net O1. The sigmoid out O1. So if you take the partial derivative on this sigmoid function, right? See, sigmoid function also is sigma of x into 1 minus sigma dash of x. Sigma dash of x is equal to sigma of x into 1 minus sigma of x. Okay, if you take the partial derivative on the sigmoid function, this is a big equation. Okay, at this moment, you just remember, by taking the partial derivative on the sigmoid function, this is what we get it. Okay, so in that case, we are taking the partial derivative on out O1. Out O1 is what? That is a sigmoid function. You are taking the partial derivative now sigmoid function. Hence, it is out to, instead of putting this in out to 1, out to 1 is nothing but sigmoid function, right? This is what is sigmoid 1. So 1 minus out to 1, right? If you substitute the values, out to 1, you already have the value, right? Out to 1, 1 minus out to 1. If you substitute all the values, 0.18 something, we get it. So what I will do is, I'll send you one write-up or document, okay, one document. It clearly explains all these things, so that you'll be able to understand very clearly all these terms, because I'm writing here. See, first thing is, how to get the value for the partial derivative of the total error divided by W5. We cannot get it directly. Hence, we need to go in the, from the right to left. That is what back propagation, right? We are passing the error back to the previous layers. But in this case, before you write in the previous layer, you pass it, you need to take the partial derivative of the total error with respect to out one, because the total error is depending on this one. And you need to take the partial derivative of dou out 1 with respect to dou net 01, because this one, the activation function, is depending on the value of our z. This z is depending on the weight of this previous layer and this one, right? Hence, we have to do, you need to go from right to left in order to solve this one, right? Fine. But here, after we, we have expanded this one, we need to find out for each and everything. What is the value? Dou E total by dou out 1. We got 0.741, right? And dou E total. So that's what I mean. What is E total? E total is nothing but E01 plus E02. What is E01? Actual minus predicted whole square, 1 by 2, right? 1 by 2 into actual minus predicted whole square, your second layer, second output neuron squared. And then finally, dou E total, right? E total. This is E total. And if you take the partial derivative of E total is out to 1, out to 1 is there here, and but here it is not there, and this becomes 0. And here out to 1 is multiplied. If you multiply out to 1 by minus 1, you will get minus, right? Sorry, the out to 1 is multiplied by 1, right? 1. So 1 into out to 1. So which value is associated with out to 1? Since there is, let's say if you use it 2, 2 into out 1, so the coefficient value is 2 here, minus 2. Since here nothing is there, out 1 is obviously multiplied by 1. So 1 into minus is minus 1. We are putting a minus 1. The partial derivative of the total error with respect to out 1 is minus 1. So target 1 minus out 1. But here we are applying the what is the power rule, right? Power rule, what we need to bring the squared value in front of this one. 2 into 1 by 2 into target 1 minus out 1. 2 minus 1 is 1 into minus 1. By solving 2 and 2 will get, this is what we get. By plugging the value, you get 0.741. We got some value, and similarly we got the value for this one. The next one is dou net 01 divided by dou w5. We need to find out the value for this. And dou net 01 divided by dou w5 is nothing but, so what is the value for this one? Okay, I don't have space here. I don't know if you don't, if you cannot see it. Yeah, I think you can see it, right? So dou net 01 dou w5 is equivalent to, so here what we do is, so what is net O1? Net O1, we need to say net O1, right? Net O1 is already mentioned. W5 into out H1, W6 into out H2, we have that value. So what we are going to do is W, right? So 1 into out H1. 1 into, let's say, 1 into out H1 into the W5, right? So into, so out H1 is nothing but, we can write this one as 1 into out H1, right? Into W5, into W5 to the power 1 minus 1, right? So W5 to the power 1 minus 1, because we are taking the partial derivative with respect to W5. W5 is there here, right? So W5 to the power 1 is there, power rule you need to apply. So 1 into W5, so 1 minus 1 will become 0. Anything to the power 0 is 1, right? So 1 into out H1 plus you need to include the B2 into 1, right? So B2 into 1. So the same thing, right? So B2 into 1 and W6 is, but here out H2 is there. We are talking about, sorry, W5, right? W6 is there. Hence, this will become constant term. In this case, this one will be dropped and this one will remain as it is. But you need to do some kind of, you need to apply the power rule, and ultimately you will get something like dou W5, right? So you will get something like 0.053, 0.593, something like that, 593. Okay. For, see, what we did, we need to find out the partial derivative for the weight W5, right? We need to find out the total error. We need to find out the partial derivative of the total error with respect to W5, but it is not straightforward, right? Because it has a dependency on the subsequent layers, right? So you need to multiply, you need to take the partial derivative first on this one. I need to take the partial derivative of this one with respect to this one. I need to take the partial derivative of this one with respect to this one. And then you need to find out the partial derivative for each and everything. E total, if you take the partial derivative of E total with respect to out to 1, Where and all out-O1 is there. Here out-O1 is there, here out O2 is there. Hence, this is constant. You cannot take partial derivative of out-O1 with respect to out-O2. Hence, this term will become zero, simple zero. And here the, you know, right, when you take the partial derivative, make sure that you are applying the power rule. So 2 cons here. Hope you understood, right? Similarly, out-O1. This is pretty straightforward, right? So in this case, it is slightly different. Here what happens is out-O1, yes, this one is nothing but activation function. Sigmoid, in our case, the activation, sigmoid activation function. When you take the partial to sigmoid activation, this is what it is. See, sigma dash of x is nothing but partial derivative of an activation function. Sigmoid activation is nothing but sigma of x into 1 minus sigma of x. So I can show you this also how we got it, but it's a big problem. In so many, it'll take longer time. Okay, I don't want to confuse you now. At this moment, you blindly think the partial derivative of the sigmoid function is sigma of x into 1 minus sigma of x. What is sigma of x? In our case, auto1 is nothing but the activation function into 1 minus auto1. Pretty straightforward. Done, right? And next one is this one, netto 1 with respect to W5. The same thing, you take it, and wherever W5 is there, you keep it. Rest you drop it. W6 here, W5 is not, drop it. And here B2, and but you cannot drop this one because bias is required. And here W5 to the power 1 minus 1, but you need to bring 1 here and 1 minus 1, and here the out H1 will remain as it is. Okay, and if you plug in the value of your out H1, right, you will get 0.593. Now, if you plug in all these value, right, for this we got 0.593, 0.593 into a dou out O1, right, 0.075, and E total out O1, right, so for the 0.741, right, 741. You will get something called 0.08, something like that. Okay, so this is what the partial derivative of your total error with respect to W5. Now you got some value, right, 0.08. The next step, what is the third step? Now you have computed the partial derivative with respect to the total error. Then last step is, the next step is you need to update the weights. You need to update because you need to update the new weight. Computing the new weight is not sufficient. You need to assign this to this one, right? That is where we use an equation, something like, yeah, this is the, so you need to update this one. So for W5 is equivalent to W5 minus, this is my old weight, 0.4 is there, right? I need to change it to the new one. So we have something like eta into dou E total divided by dou W5. What is eta? Eta is something like, the learning rate. You remember I discussed about step size, right? In the other slide, right? Steps in the gradient descent slide, I showed you the step size. You can assign some value randomly, 0.05 into, for this we got 0.082, right? And the W5 is, the current value of W5 is 0.40. You need to subtract the new weight by multiplying with the eta value, which is nothing but the step size, from your current weight in order to get the new weight. This is how we get the new weight. Similarly, if you perform take the partial derivative with respect to W6, W7, W8, you will get the W6 value, some value, right? W6, new weights for W6. So this is how you can get the new weights for each and every weights. You understood, right? I took one example, W5, right? In the W5, you cannot take the partial derivative on the total error with respect to W5 directly. Instead, you need to apply the chain rule. This is called your chain rule. So in this case, whatever you're going from right to left. So here you took the partial derivative dou E total with respect to dou out 1, and then dou out 1 with respect to dou net 1, and dou net 1 with respect to dou 5, right? So if when you go by this, you get, so, and then this is how you get it. and you need to find out the values for each and everything and multiply all the things, and then multiply this value by eta 0.05 step size. You remember what is my step size? Can I keep 1 feet? My step size should be 1 feet or 1.5 feet. You remember in the gradient descent I showed you the image, right? This is the one, right? The step size. Can I keep 1 feet or can I keep 2 feet? If the step size is too big, the chances are that you may not reach, you cannot get the optimal, you may jump from year to year. You just assume that you are jumping from year to year, jumping from, right? You are taking a long jump here. What will happen instead of coming here, you jump here, overshoot. This is called overshooting problem. Okay. So what will happen is, for that, what we are doing is, right, we are updating the weights here. Okay. So very easier one and very easy to understand. But only thing is, you need to take the partial, take the pen and paper, and you compute it. Very simple one. Similarly, you give it a try for the hidden layer also. See, in the case of hidden layer, the output of this first hidden neuron, right? Look here, the line is going here. This line is going here. The output of the hidden layer one first neuron is impacted by both this one, contributed to both E01 E02. That's why in the interview they'll ask you this question. We are talking about this one. Why do you take into account of the total error instead of instead of this? You should have taken only E01. Why E total is required? Because this E01, right? For this, the output of this one is this one, and the output of this one goes to this one also. And again, for this, right, the input is this one and this one, and for this one and this one. Hence, we are supposed to take E total, because for each hidden neuron, right, it is connected with every other neuron. Hence, you cannot simply ignore this one and sorry, you cannot ignore. See, in this case, right, you can the case of total error, right, you cannot ignore this line and this line, because this line is connected to this one. Hidden layer 2, so hidden layer second neuron is connected to this one. How can you ignore this one, right? Since it goes here and also it contributes to this one, you need to consider E total. That is the reason why we have taken E total even in this previous case. You remember I mentioned do E total, do W5. Instead of taking this one, do E01, do W, we should have taken, because the problem is it is all interconnected, right? The first neuron in the hidden layer contributes to both these two neurons, right? Hence, we need to take a E total, only then you will get the correct one. But in this case, right, the output of this one is depending on these two things. Look here in the previous slide, right? This total error is depending on this one, and this one, the output layer one. But if you take a partial derivative of W1, right? So let's say W5, and similarly W5, W6, W7, W, you can take it. If you go to this first layer, the input layer, right? But this one is depending on the output of this one is depending on this one and this one also, because it is contributing to these two things, and also these two are depending on net O1. Net O1 is depending on W1. That's the reason why if you see here, do E total with respect to W1 is nothing but do E total divided by do out H1 into do out H1 into do net H1 and do net H1 into do W1. Okay. So now similarly, right, you need to find out the value for each and everything by taking the partial derivative with respect to the corresponding values here. So dou E total by dou out H1 is nothing but dou E01 divided by dou out H1. My cursor is not moving. Yeah, the dou E02 divided by dou out H1. Right. So you need to take the partial, give it a try this one. Okay, if you are not able to do it, you let me know, right? But by doing so, right, you will get the value, new values for W1. Look here. So 1 second. By doing so, you will get the, when you take the partial derivative with respect to dou E total with respect to dou W1, you will get the new value for the W1, new value for the W2, W3, W4, and so on. With the new value, right? If you compute the error, you need to compute the error. How will you compute? So this value into this one, applying the activation function, this value into this one, apply the activation function, end to end you need to do it. When you do it, what error you are getting it. If the error is less than this value, let's say my error in this case, right? What was the error here? Yeah, 0.01 into this is what I mentioned, right? So 0.01, yeah, 0.0, 0.75, right? 0.741, something like that error. If my, with my new weights, what is my error? For W1, W2, you assign the new weight with that. If the error is even slightly lesser, then there is an improvement. But doing it with one or two iteration is not sufficient. When it comes to neural, what we do is we do this iteration 100 times or 1,000 times also sometimes. Okay. So in that case, when you iterate this multiple times, the chances are that the error can drop significantly or it can drop substantially. So here the question is, how many number of iterations should I use it? How many number of iterations should we use it? Uh, that is one important question. Okay. So what I would say is you can watch my video, epoch, batch size, iterations are related. One video I put it in my channel. Okay, I'll share the link also. You just watch it. What I will do is currently, right? See, this is how the back propagation works. Okay, you need to take the partial. First step is you need to find out the loss value, loss function. Second one, you need to find out the partial derivative with respect to total error. And third one is you need to obviously update the weights with the new value. That's all, very simple one, right? These three steps, you need to use it in the case of back propagation, very simple one. And what you do is, yeah, the next step is I will just show you in Python how to implement neural network, okay, using Keras. We have something called TensorFlow. TensorFlow also will touch upon the next week, Saturday. You can implement the neural network using something multi-layer perceptron, something like that. But usually we use TensorFlow or Keras to implement neural network. Keras is an API for TensorFlow. What is TensorFlow? TensorFlow is a framework. Okay, it is developed by Google. Okay, using TensorFlow you can implement machine deep learning algorithms. Okay, and so the TensorFlow, this is the one is developed by, package is developed by Google. Okay, and also we have something called Keras is available. Keras is an API for TensorFlow. You don't have to understand the uh, the mechanics of how TensorFlow works, right? You don't have to write too many lines of code. The Keras is an abstraction. It's an abstraction for TensorFlow. You don't have to write using Keras. You don't have to write too many lines of code. With Keras, you can write less number of codes in terms of implementing your deep learning or the traditional neural network model. See here, I imported the TensorFlow as to, but you need to install TensorFlow. Okay, pip install TensorFlow. Okay, and this is the so you need to go to your operating system and command prompt and install it. Okay, and the next step is install Keras also. Pip install Keras and import all these things. Import TensorFlow as TF. This is your alias and Keras.models import sequential layers in input layer dense SGD. This is nothing but your optimizer, right? The stochastic gradient descent. See, in the gradient descent itself, there are three variants. Other one is batch gradient descent. What I discussed was batch gradient descent. The stochastic gradient descent is it takes only one training example for each iteration to find out the optimal the value for the parameters. Okay, we have something called light gradient descent. Light gradient descent in between this. You see, in the case of batch gradient descent, supposing you have 100 million records or the data set, right? For each and every step, you remember that image, right? The downhill, right? From the hill, if you ascend, each and every step, right? It takes the entire data to compute the the value for the your parameter, right? But instead of taking the entire value, stochastic gradient, it takes only one record, but taking only one record is not much helpful. There's something called light batch gradient descent, something is there. So there it will take the subset of your data set. With that, it will find out the optimal value for your theta 0 and theta 1. Okay. This is an optimizer. Basically, it is an optimizer. See, we use gradient descent algorithm as an optimizer to optimize the cost, right? That is why we call it an optimizer. Instead of using gradient descent, batch gradient, I used SGD. And so here I use, ignore these two steps, okay, callbacks, everything, okay. And my data set, 1,196 records are 18 columns are there. Now I'm going to create the instance sequential. Okay, sequential. Okay, I'm creating instance here, sequential. Okay, what is sequential? That means I'm telling Keras to create the layers for the neural network algorithm layer by layer. Okay, next one is model.add. I'm going to add first layer. What is the first layer? The input layer. You remember, right? The input layer, hidden layer, output layer, right? Three layers I'm going to create it here. The first layer, 18. So what is 18? 18 is nothing but 18 neurons. See, in our example, I showed you only two neurons, right? The age and income. But in this case, in the case of churn model, 18 columns are there. Hence, I mentioned 18. 18 neurons you create. Input dimension is equal to shape of one gives you this one, right? 18. So this is the one. Input dimension is 18 and 18. And activation is sigmoid. Okay. And the next one is dense is 8. So I'm going to give some value, right? In the hidden layer, use only 8 neuron. That is sufficient. And there is a formula for this. We'll discuss this later. Okay. And because when I discuss about CNN, I'll explain everything because it involves a lot of formulas out there. Okay. Here also the hidden layer, I'm using sigmoid. And then finally my output layer. Output layer only one, right? I want to emit only the only one predicted label in this case. Okay, so hence it is going to be one only. Activation is sigmoid. So now model dot summary, if I give, so dense 6, the output shape is 18, and then the hidden layer 8 neurons in the input, right? 18 neuron will be there. Here 8 neurons will be in the hidden layer, and here 1 neuron will be there. Okay, so that is how we'll get it. And what I'm going to do is, the next step is, see here I defined my neural network architecture. Okay, architecture. The next one is I'm going to use something called model. Yeah, the model.compile. So this step is very important. Okay, because in the case of deep learning, this is the syntax we follow. Okay, model.compile, you need to specify the loss function. In the case of linear regression, the cost function is error. The mean squared error, right? 1 by 2 or 1 by n into actual minus predicted whole squared. But when it comes to classification problem, especially the binary classification problem, the loss function is not the mean squared error, right? In the case of loss function, in the case of, binary classification, we call that, we use something, we call that as the loss function as a binary cross entropy. Binary cross, this is very important. The interview they'll ask, binary cross entropy. Okay, the loss function. So you remember I explained this one, log of predicted value of y the loss function for the classification, binary classification problem. Okay. So 1 minus 5, y, the actual, see the y is actual value, right? Y is actual value, log of predicted y plus 1 minus y into log of 1 minus predicted value of y. This is the cost function for your binary classification problem. In the case of linear regression, the cost function is mean squared error. But this is not a regression problem. This is a classification problem, binary classification problem. Hence, see, this data set is related to churn, right? Whether the customer is going to churn or not. Binary classification problem. Hence, the loss function is binary cross entropy. You need to specify it explicitly. An optimizer SGD, stochastic gradient descent. Metrics is accuracy. You know what is accuracy, right? We discussed the length and breadth of accuracy, precision, recall, everything. Next one is after you do this compile. Let me expand this one and see. Oh, I need to execute it here. Okay, here let me see. Here the POC. Okay, I just stopped it in between. Okay, next one is model.fit. First, you need to define the architecture using sequential, right? You need to stack up. The first you need to define the input layer, hidden layer, output layer. Next, you need to compile. As part of the compile, you need to tell which loss function it has to be used and what kind of optimization, right? Or whether it's a gradient descent or stochastic gradient, and what kind of metrics that has to be used. And next one is model.fit. See here the model.fit, right? See here all the independent variables. This is my dependent variable with nothing but my label, right? Yes or no, right? Or 0, 1. 0 is non-churner, 1 is churner. Epochs is 100 and batch is equal to 4. Right, epochs is 100, and don't specify too much of value for epoch, right? Specify 5 or 10 because your system will hang, and batch size equal to 4. And next one is model dot evaluate accuracy. To find out your model accuracy, you need to use evaluate. So model dot compile, model dot fit, and model dot evaluate. This is mandatory. You need to use these steps for even for deep learning models. Right, so this is to get the accuracy, right? This is the one will give you the accuracy, and also you can find out the weights. The neural network I showed you in my PowerPoint, right? The weights, these weights 0.15, 0.20, what weights assigned to each and every layer, right? So you can say model dot laser get weights. You can see the weights for the Bayesian for bias, right? What values assigned to bias and what weights assigned by the algorithm to each and every layer, hidden layer, between hidden layer to input to hidden and hidden to output layer, right? All the things you can find out here. You just go through on this one, okay? And we'll explain. Anyhow, I will review these things when I explain you about the convolutional neural network in detail, okay? And the questions are like the interview question: how do you decide the architecture? Look here. Here you mentioned about one input layer, and you mentioned a one hidden layer, one output layer. So why only one hidden layer, and why only 8 neurons in the hidden layer, right? So why can't it be 18, similar on par with input layer? Everything we'll discuss it in detail as part of your convolutional neural network. Okay. Hope you understood, right? You just go through on my channel analysis final. Here I, the fact, because this file, I use it for making a lot of changes. Look here, I got some error and all, right? But the final has no error in it because this is a working copy. You can do it. And TensorFlow, here I used Keras.callback. This is basically, see, TensorFlow, they are giving some dashboard. Okay. Here you can view when you execute your model, right? The model output, you can view it here. I have some issue here. One second, it is not coming out. Anyhow, next week I will start with the TensorFlow basics. That time I will show you how to use TensorBoard. And next, what I will do, followed by this, we'll jump into the convolutional neural network. And that time I'll explain you all this, what is epochs, batch size, everything. And it's already 11:25, okay. And also we'll complete RNN next weekend itself. Yeah, we need one more weekend to complete the NLP and other part. So not a problem. See, with this itself, right? If you start practice it along with my assignments, whatever the assignments I gave it to, right? You're good to go with understanding all these concepts. Okay, and apart from this Kaggle, there are some data sets that I'll show you. I'll point you to certain case studies in Kaggle. You start work on that. That one will definitely help you to understand the in and out of machine learning. And even there are some good Kaggle assignments with solutions for image classification. I'll share you the link and all. That one will help you to understand the the algorithms and the way how other people, the Kaglers, they wrote the logic to solve different for the same problem, how they use different approaches to solve it, right? So I'll send you those links also. Start work on it. That way you can solidify your understanding around these concepts, and also you'll be understanding from the technical point of view what other packages you can use it, right? So you will get a complete understanding about it. Okay. And even PyTorch is also gaining a lot of popularity, like scikit-learn, TensorFlow, right? Like TensorFlow, PyTorch is also meant for deep learning algorithm. Okay, that is also gaining a lot of popularity. But if you know TensorFlow is developed by Google. Even my students, right? A student in the sense in Tiger Analytics is the big data practice head. You know that guy. He got certified recently. I saw in LinkedIn. Google certified professional, Google certified machine learning engineer. Right. In that, you mentioned that TensorFlow they ask a lot of questions. Okay. So hence, if you focus on TensorFlow, that is more than seven. But side by side, if you are looking for a job, right? If you update your profile with multiple skill sets, including the PyTorch, also it can add more value to your profile, more weightage to your profile. All right. Fine. Hope you understood, right? If you have any questions, you just shoot me, or else next weekend, right? We will discuss if you have any questions. Meanwhile, start work on the assignments. I will urge you to start work on the assignments. If you don't work on it, you will not be able to understand, or at least take a look at the solution link which I shared it for the regression problem. Okay. See, the regression problem, it is already there. Many blogs are there for the assignment which I gave it to you in the internet. But one challenge is the adjusted R squared. For that data set, you will get maximum zero point 0.7 only, zero point 0.7 or 0.72. But I did some tuning. With that, I'm able to get 0.85 adjusted R squared. Right. The challenge for you is increase the adjusted R squared to 0.85. Okay. And if you look at my R script, right, the link which I shared it in my website, right, you go and take a look at my R script, you will get a clue for that. Okay, you'll get a tips for that. With that, you implement it in Python. And see, a lot of blogs are available for the housing price prediction. Okay, you can also do googling and execute it step by step, understand it thoroughly. You don't have to rely on my code only. But the point here is adjusted ask has to be increased. How you can increase it? That you cannot see it there, but in my R script you will find it. Let me see how many of you are able to get a clue from my script. Okay, how the adjusted got increased. Okay, to 8.85. All right, it is already 11:30. We'll circle back next weekend. Hope next weekend is being a long weekend. I don't know how many of you are available. You let me know, based on which we'll schedule it. From my side, you know very well, I work for the retail, big box retailer. We have a lot of work for Christmas, though I have a lot of work since I slogged for both Black Friday and Cyber Monday, right? I can give some excuse. Next weekend, we'll try to wrap up everything if possible, okay? In fact, we will start little earlier. I'll try to complete NLP also the next weekend itself, all right? Any
Thank you,
questions?
Satya.
Yeah, okay, bye-bye, take care. Any questions? Okay, since you don't have any questions, I'm going to wrap up now, okay? See you next weekend.